Till now we discussed on the waveforms on the secondary side of the forward converter, which was mostly like the buck converter. Now let us look at the primary side, this switcher and the core reset issue. Let us draw the waveforms related to that and then try to understand that. So I am going to divide the time again into 4 parts, where you have DTS. DTS, the time during which the switch Q is on, 1 minus DTS, the time during which switch Q is off. DTS, again Q is on, 1 minus DTS, Q is off. So let us first consider the voltage the current waveform through this diode, and that is what will actually get reflected onto the primary. So let us mark here the primary current IP. Remember that primary current and IQ are same only during the time when Q is on. Then you have IP and IQ same. The moment Q is off, IQ becomes 0, but IP doesn't become 0 because there is a freewheeling current that will happen in this direction. So therefore IP and IQ are not strictly same. During 1 minus D time, IP has some finite current, IQ is 0 during that time. So what is IP? IP is the reflected secondary current, and at the secondary what is flowing when the transistor Q is on is ID1. So N times ID1 is what is supposed to be reflected onto the primary, the load reflected part. So let us take N ID1, which is ID1 into N, the load reflected part flowing through the primary. This is one component. So we know that the load reflected part, during that time the inductor current is rising, and this is how the current wave shape will look like, and this we have seen before. And if you take the level at this point, you know that that is N times I0, again load reflected part. Now next we should understand that this is a transformer, and there is some current needed to magnetize the transformer, and that is the magnetization current. So a magnetization current also will flow through this primary, and that should be added to that to get the total IP. So what will be the magnetizing current? I will say IP mag. When Q is on, Vi is applied across the primary winding. It's a constant voltage. So the magnetizing current from the Faraday's law, Vi is equal to Lm di by dt. The magnetizing current will have a slope of Vi divided by Lm. So it will start from 0 like that. It will have a slope of Vi by Lm, Lm being the magnetizing inductance. During 1 minus D, I will explain later. For now, we will leave this part, and again it will start from 0. During this time, we have to reset the core. We have to reset the core and bring it to 0 so that it will again start back again. In the meantime, let us also draw, before we draw this portion of the magnetizing current, let us draw what will be IP. IP is the primary current. The primary current will be having two components. One is the load reflected part, which is NID1, and the other one is the magnetizing part, which is IP mag. These two will add up together to form IP. So this part, this magnetizing part, I am actually showing this a bit zoomed. It will actually be much smaller as compared to the value of NID1. So let us say this is the NID1 part, which I am writing down here. This part you can add it up here, starts from this value and then gradually it will go up like that. Same at this DTS period also. So this will be the IP. This green portion will be the total added up IP value during the time when Q is on. when Q is off, you will see that IQ becomes 0, but IP will start freewheeling in this path. So it will freewheel in this path because inductor current cannot become 0. There is this resistance Rm and there is a mutual inductance Lm. Lm by Rm will be the time constant. So with that time constant, exponentially IP will decay. Likewise, here also you will see that it will decay in this fashion. So now what will be the IP? In the IP waveform, this same thing will repeat. You will see a drop because the moment Q is off, the reflected component vanishes, ID1 component vanishes, that becomes 0, and only the IP MAC component will come into the picture, and that's what we will find in this. So the total IP current will look like this, drawn thick in a thick green line. This will be the IP current that will be flowing through the primary winding. Let us now see also what is the voltage across Q, VCEQ. So let us draw one more axis here and see VCEQ. During the time when Q is on, you know that this is 0, and at the moment when Q is turned off, you will see that there will be a sharp rise. What is that value? We will see that. And then afterwards, post that rise, you will see that this is VCC level. The VCE will start decaying down to VCC level. Why does this happen? You see that moment this is switched off, this is freewheeling in this fashion. So there is a drop across the diode, forward drop across the diode. There is a drop across this Rm, IP into Rm, current is flowing in this direction, IP into Rm. And there is Vi. So Vi, drop across Rm and the diode drop will all be reflecting here when this shoots up. And then IP current is decaying. As you see here, it is decaying exponentially. So the drop across Rm should also decay exponentially. Therefore, you see a decay exponentially, and once the decay is complete, it will settle at Vi. Because once this is off, it is only Vi that will come at this point. So this is how the voltage across the BJT will look like, and then it will repeat again the next cycle and decay in this fashion. So this point I would like to say is the VCEQ, which is equal to Vi plus this diode drop, VDM, forward diode drop around 0.7 volts, plus the current flowing in this direction, plus minus here you have Im into Rm. If I say this value Im peak at that point, Im into Rm will be appearing across. So this will be the voltage that will come across at this across this transistor Q during the time, at the moment when it is being switched off. And then further on during the time 1 minus dTs, it will start decaying down like this because Im is decaying down. Now this decaying time constant is equal to magnetizing inductance Lm by Rm. Now what should be the value of Rm? So let us say 5 times time constant, 5 times Lm by Rm is the time constant which says that this would have reached steady state. It would have reached 99.9% of the final value. So by that time, this core would have reset. If Im comes down, magnetizing current comes down to 0, then you can say that the core is reset. So in 5 times time constant, the core would have reset so that it can take up the next cycle. So this should be less than this time 1 minus dTs. So before the off time is over, the core should have been reset. So this is one relation. Another relation is the voltage across Q, VCEQ. So the voltage across that is, as we saw here, Vi plus VDM plus IMRM. This is the peak voltage that the device will see, and that it will see at the point of switch off. Now that should be less than VCEO rating of the device. This is the second relationship. Now these two inequalities, using these two inequalities, from this you can see that Rm should be greater than phi Lm by 1 minus dTs. Ts I will replace by switching frequency, so I will say phi Lm Fs by 1 minus d should be less than Rm. Rm I have taken to the other side, and Rm should also be less than. Now if I take this relationship, VCEO minus Vi minus VDM by Im should be greater than Rm, or Rm should be less than that. So VCEO minus Vi minus VDM by Im. So this is the value of Rm, which will be the upper limit. This is the value of Rm, which will be the lower limit. Rm should be a value which is in between in this range. So this is the design equation for Rm selection. Now what is the power rating of Rm? So you see that when this is switched off, there is a current Im starts freewheeling through Rm. The energy in the magnetizing inductance at this point is half Lm Im square. Now that much amount of energy has to dissipate. Then only the core will reset. So that has to dissipate only in Rm, because Rm is the only dissipating element. So let us say power rating of the Rm can be found out from half Lm Im square amount of energy has to be dissipated every cycle, every switching cycle. So you can say this is equal to half Lm Im square into Fs, and this is the power that will get dissipated in Rm. Whatever may be the value of Rm which you have chosen in this range, because this energy, the energy here is independent of the value of Rm. So this is the power rating choice that you have to do for Rm. So with this you can now say that all components of this forward converter circuit with core resetting feature can be now implemented in this fashion and also simulated. There is one important variable that we will not be able to measure and see on the oscilloscope, and that is the flux inside this core. We have been talking of core resetting, the core in the flux which is to be reset, but we will not be able to see the flux waveform. But indirectly we can know how it looks like. So let me try to plot an estimate of the flux. See the flux in the core with the symbol phi, and let us try to plot that one. Now we know from Faraday's equation that Vp, the voltage across the primary, is equal to Lm, the magnetizing inductance, dIm by dt, or d magnetizing current by dt. It is also equal to N or Np, d phi by dt. So from this basic fundamental equation we see that Lm dim by dt is equal to N d phi by dt. Lm is a constant, N is a constant, Vp is fixed for the period of the time when Q is on. Therefore, d I mag by dt, demagnetizing current by dt and d phi by dt will have the same wave shape and therefore same slopes, and therefore I magnetizing current and flux in the core should also have the same wave shape. Therefore, the flux within the core will take the same wave shape as IP mag that we have drawn here. So let us draw that, the same linear rising and fall, because when Vp is fixed constant when Q is on, Vp by N will be the rate at which the flux will rise, and it will fall exponentially because the current Im is falling exponentially. And again, the next cycle it will go in a linear fashion to a max value and then fall exponentially. This maximum value is phi m. So this is how the flux waveform within the core may look like if you are able to probe it and see it on the oscilloscope. But we are able to get this wave shape indirectly through the Faraday's law. So you see that the flux rises and then the flux is reset. This is the core resetting action. The flux in the core gets reset to 0 and it is ready for action the next cycle when it again rises, and then during 1 minus dTs period the flux is reset again. So this is core reset in forward converter. We have been discussing about this forward converter with this type of core reset. Now this is a lossy core reset. The reason being that there is some dissipation occurring in Rm, and we calculated that the dissipation that happens in Rm is half Lm Im square into Fs, meaning half Lm Im square is the energy stored in the magnetization, and that half Lm Im square must be removed every cycle, and therefore half Lm Im square Fs is the amount of power dissipation in this Rm. So this will bring down the overall efficiency of the forward converter. So let us discuss another method of core reset where it is lossless. So lossless core reset. So what we do is first we remove this and then let me make some space, and I will introduce one more winding which is tightly wound to the primary 1:1. In fact, bifilar wound. You take the primary and this winding, which I will call as demagnetizing winding because it is used for resetting or reset winding. You take them together and wind them so that there is minimum leakage as possible. And then you attach a diode like this, and the other end you connect it to Vi or VCC, and you place the dot polarity in this manner, opposite dot polarity. Okay. Then let me put this as 1:1 and let me push this back here. Okay. So now this is the modified forward converter where you have removed the lossy core reset circuit and you have interposed another winding, no resistance, only the winding, but there is a freewheeling diode. Now how does this become lossless? Let us see how the core reset action is performed and how it is lossless. So this winding is normally termed in literature as the demagnetizing winding or simply the reset winding because of the job that it does. Now just like you are measuring the voltage Vp here in this fashion, Vs here in this fashion, I will measure the voltage across the demagnetizing winding and let me call that one as Vd. So now it will be appropriate to look at some waveforms to understand the operation of the circuit. Again, I am dividing the time into 4 parts: dTs, 1 minus dTs, dTs, and 1 minus dTs, 2 cycles, 2 switching cycles. dTs the time period when Q is on. So now first let us see the 2 waveforms Vp and Vd simultaneously. Vp and Vd. Now during the time dts, Q is on. So when Q is on, the entire Vi is coming across the primary coil with dot end positive, non-dot end negative. So if that is the case, in the other windings, you will see the dot end positive, non-dot end negative for the Vd in this fashion, and dot end positive, non-dot end negative in the secondary. And the secondary operation, we know it is the regular buck converter operation. We will not be discussing it now. Let us focus only on these two coils, the primary and the demagnetizing coil. So during that time, Vi comes across Vp, call that Vi, and as I am measuring in this fashion, the dot end being positive, it will appear minus for Vd, minus Vi. So because it is minus Vi, the diode is reverse biased because there is a minus Vi and there is also a Vi of the supply. So minus 2 Vi comes across the diode. The diode is reverse biased, no current flows through it. But it is also interesting for us to look at what is this diode current ID. So let us also have one axis here for the diode current ID. I would also like to look at the magnetizing part of the IP. I'll come to that later. So the diode current ID, because the diode is reverse biased, it will be zero current at that moment of time. Now if I take the magnetizing part of IP, recall that IP is consisting of two parts. One is the load reflected part, that is N times ID1, and the magnetizing part, IP mag. Together they form IP. So consider only the magnetizing part, IP mag, which is a kind of a ramp in this fashion, which is having a slope of Vi by Lm, the slope. Now during 1 minus dTs, Q is switched off. The moment Q is switched off, the current here is immediately brought to zero. So there is a large di by dt, negative di by dt, and therefore there will be reversal of potential across the coils. So let us mark that reversal of potential. Potential non-dot end becomes positive, dot end is negative, non-dot end is positive, dot end is negative. Likewise on the secondary side. This secondary side, now here the inductor is freewheeling. This is plus and minus in this fashion. This diode is reverse biased, so the entire secondary is like open circuited. We will not talk about that. We will talk only about these two. Now here if you look at the non-dot end is positive, and this will keep this will become as positive as it can pump against this Vi and make this diode forward biased, so that the diode is conducting for freewheeling action. So if I draw the voltage source Vi portion also here, you will see that there will be a conduction of current in this path like that, and comes through this against the source Vi and reaches here. So from this plus, it goes in against the source. So if the diode is ideal, the drop just a bit more than Vi is what this will be needed to pump current into the pump current for resetting the core. So this is the freewheeling action that will happen. So what is the voltage across Vd and Vp? So across Vd, because this is a diode clamping, plus and minus, this coming directly across Vi, it will be Vi. In this measured in this direction, non-dot end positive. So in the case of Vp, you will see that it is negative, minus Vi, because this is 1:1 turns ratio. This is 1:1. And what happens to ID? See that IP had charged the flux up to that point, and now ID will take over from there and discharge during that time with a slope of minus Vi by Lm. This charged with Vi by Lm, this will discharge with minus V by Lm. So therefore, if this has taken x seconds, this should also take x seconds. That is why we say that if this has taken ts by 2, this would be ts by 2. You should give the same amount of time for it to reset. Therefore, you cannot have a duty cycle greater than 50% in these type of converters. But it's not a disadvantage because you have n as a degree of freedom where you can adjust the voltage. So next cycle behaves in the same way. You have the repeat, and during this portion there is no ID, there will be IP mag, and then ID comes down in this fashion. So IP magnetizing flows only during DTS portions. ID flows during 1 minus DTS portion as the freewheeling part. If you look at the flux within the core, the flux within the core will have the same profile as ID and IP mag. It will take the profile of IP mag during the DTS period because that is the magnetizing current that is flowing, and during the 1 minus DTS period, the magnetizing part is flowing in the freewheeling portion of the demagnetizing winding, and that will be this part. So this is Vi by N, this also is Vi by N negative because it is falling. So this repeats. So this will be the nature of the flux. The flux builds up and the flux resets during 1 minus D. Flux builds up, flux resets during 1 minus D period. Because the slopes are same, you need to give at least that much same amount of time for it to reset. Therefore, limiting the duty cycle for this type of converter max to 50%. So this is the way the core reset functions in this. Note 2 points. This windings here, the primary winding and the demagnetizing winding should be 1:1, and they have to be tightly wound together, wind them together. That's called bifilar winding. So that the leakage inductance is minimized. The reason is that if there is a leakage here, that portion is not covered for mutual inductance for demagnetizing. So that can cause a large spike across the device when it is switching off. That can also be avoided by having a snubber circuit, which I will discuss later when I am discussing devices. But I could also provide you with a quick solution to avoid even the leakage inductance shortly when I am talking of using dual switch or 2 switches for the forward converter and remove this magnetizing portion. Then we can still get lossless core reset and avoid the leakage inductance issues also. We can do lossless core reset with dual switch forward converter also. So let me briefly describe the dual switch forward converter and explain to you how this lossless demagnetizing can be done. So this is the circuit of a forward converter without any demagnetizing, without any core reset, and let us introduce core reset now. So let us remove the VCC for now, and then here I will introduce another switch, another BJT, and this is Vi. Let me call this Q1 and this is Q2. Okay. Now these 2 switches are switched on simultaneously. Okay. Now I will add 2 freewheeling diodes. One diode freewheeling from here to Vi to VCC, and another diode from here down to ground in this fashion. I'll explain to you how the current flows. Let us also visualize that there is a supply here. So let us place that supply because we have placed the label. So let us visualize to understand the current flow. Now let us consider the situation DTS when Q1 and Q2 are both on together. So when they are both on together, you will see that this is on, so Vi, this is plus and this is minus. On the secondary side, this is plus and minus. Secondary side operation we know is buck converter operation. So let us see how the current flows here on the primary. So it starts from here, goes in this direction, comes like that through the ground and back again to the power supply. So this is the path of the current flow during the period DTS. and where the voltage across the primary is plus minus dot end positive, Vs dot end positive, buck operation follows. Now what happens when you switch off Q1 and Q2? So when you switch off Q1 and Q2, there is a cut in the primary current, meaning the primary current is cut off to 0, but we cannot allow cut off to 0. There will be a reversal of polarity. So first this polarities will reverse because of the minus di by dt, and there has to be a path for the IP current flow in the same direction in the coil. So let us start from here. IP flows here. Now as Q2 is off, current flow in this direction through this diode and then into the supply. So I am indicating the supply here, goes into the supply, and this comes in this direction through this diode up there again and then down, and maintaining the same direction of current flow in the primary. Only now the dot end is negative, non-dot end is positive, so it is demagnetizing. So this coil is acting like a demagnetizing winding during the 1 minus D period, because the secondary side is open, this diode is off. So this because the same winding is operating as demagnetizing winding, there is no leakage inductance problem because everything is included here in primary reflected, and you will not have leakage inductance spikes due to the leakage inductance spikes on the two switches when they are off. So this is the path. This is the path where the demagnetizing current will flow, and because if you consider diodes as ideal, this whole Vi is coming across the primary plus minus in this direction. So you have to allow the same time, because again it is 1:1. The magnetizing is happening at Vi by N. The demagnetizing is also happening at the rate Vi by N. Therefore, you have to allow the same amount of time for demagnetizing as you are allowed for magnetizing, and therefore this is also limited to 50% max duty cycle. This is not actually a serious limitation because of the N here. You can adjust the value of N to get whatever required output voltage. So this is the dual switch forward converter. You have removed the windings, but you have included one extra diode and one extra switch, and an extra control switch means extra gate drive for that.